All right, so in this video, we're going to talk about exponential and logarithmic functions. So the next couple videos that I put together that you watch will be everything for both the exponential and logarithmic functions. I like kind of handling them together so that you can see the connections between them all. So we'll start here with a little bit of a review. So if we look at an exponential function, remember from your college algebra days, that's going to be of the form a raised to the x, where this a is of course a real number. It's got to be bigger 0 and it can't equal 1. So the graph of the exponential looks something like this, where we've got our point here of 0, 1, and we also have an asymptote at y equals 0. Okay, so some basic characteristics of the exponential function. The domain is going to be negative infinity to positive infinity. The range is going to be 0 to positive infinity. We don't include that 0 because that's where that asymptote is. It's increasing on its entire domain, so negative infinity to positive infinity. We also know the limit as x approaches positive infinity of our exponential function would be positive infinity, and the limit as x approaches negative infinity, well, that's the one as we go to negative infinity over here that we would limit out at our 0. So that would equal our 0. Okay, so there's just a nice basic review of the exponential function. And we're going to go ahead now and define what the number e represents. Okay, so we know that e, which is just a constant, it's approximately 2.71 whatever, we're going to define that now as the limit as x approaches 0 of 1 plus x raised to the 1 over x. Now that seems kind of random, but what I'd like you to do is go into Desmos and actually graph that function. Graph this 1 plus x raised to the 1 over x, and you'll see as you approach 0, you do end up at e. And so this limit will come into play several times throughout this course, but that's how we're going to define what e actually is. Now, moving forward from that, the first thing we're going to talk about in terms of calculus at least, the derivative d dx of e to the x is going to be the easiest derivative you've ever done. It's just e to the x. So the derivative of e to the x is itself, which is actually pretty interesting. We'll prove this. We're not going to do it right now, but we will prove this, and I'll show you why it is what it is. The other thing I want to mention before getting into an example is our chain rule. If we have base e raised to something other than x, maybe a different function, the chain rule then would be the derivative of the outside, which would just be the e to the whatever is what I would call it, back times the derivative of the inside. Okay, so these are your two new derivatives now in Calc 2 that we would not have seen in Calc 1. So we've got a basic review of the exponential function. We've defined e, the number e, as this limit, and then we've got our new derivative. Derivative of e to the x is itself. So I'll go ahead and now clear the screen and we'll take a look at an example. Okay, so we've got our function here. We've got e raised to the square root of x plus the square root of e to the negative x. And we're told to find the derivative. Now, before I do that, I probably want to clean this up a little bit to avoid any unnecessary work or any unnecessary mistakes for that matter. So f of x is going to be the same thing as e to the x raised to the 1/2, and then plus e to the negative 1/2 times x. So remember, this square root here, this is a rational exponent of 1/2, so that's what I've done there. And then for this guy, this whole piece now gets raised to the 1/2 power, and so then when I multiply that into the negative x, this is what I end up with. Okay, so now it's going to be much easier to take this derivative. So f prime, since this is going to require a chain rule, we're going to have the derivative of the outside, which is just copying down the 1/2, and then back times the derivative of the inside, which I would refer to as the exponent portion now. So that's going to be a 1/2 x to the negative 1/2. And then for that second term, same thing. Write the e down. So negative e to the negative 1/2 x back times the derivative of the inside, which would be the negative 1/2. So This would be considered an unsimplified derivative. In a lot of our written work, I will ask for unsimplified derivatives, where you essentially just stretch out all of the derivatives parts without doing anything more. So again, this is an unsimplified derivative for a problem like this. Okay, so now we're ready to talk about the logarithmic function. And I've got up here just a basic summary once again of some things we talked about in the last section, and hopefully you saw in college algebra. Since that exponential function is 1-to-1, and we know that by looking at the graph, it would pass the horizontal line test, therefore f is invertible. So we also talked last time about this general notation here about the inverse at x equaling y if and only if the function at y equals x. And so that's where what you might have seen back in college algebra dealing with logarithms in terms of how to manipulate them. This would be your log base a of x equals y if and only if a raised to the y equals x. So hopefully you've had a lot of experience with that, and then now it's starting to come together maybe in a little more rigorous sense. Now this a that we're talking about right here, this a is this a right here. So the conditions have to be the same. A's got to be a real number, A's got to be bigger 0, A cannot equal 1. So those conditions on A for the exponential would be the same for the logarithm. All right, so now let's take it a little further. I'll say by substitution, we know that A raised to the log base A of x has to equal x. And this is for all x bigger than 0. I say substitution because we know that y is this thing. So if I substitute that up there, I get my a raised to that log equaling x, which is what I have right here. I also say that where x has to be bigger than 0, we know that x has to be bigger than 0 because exponentials are always positive, which also puts a very strict domain restriction on our logarithmic curve. Okay, so I want to draw two graphs for you real quick. The first one is going to be the exponential and logarithmic curve on the same xy plane. We know that the exponential curve looks like this, and it goes through the point 0, 1. Right, so that's the exponential curve. We also know that since they're inverses, they have to be symmetric about the line y equals x. So my reflection now is going to make my logarithmic curve look like this. And because we interchanged our points, we would get the point 1, 0 out of that. So it's important to see the relationship there as well, kind of together. But that picture is pretty messy, so I'm going to redraw just the logarithmic graph over here for you. So here's that logarithmic curve. This is y equals log base a of x. Our point here is 1, 0. And then I now have a vertical asymptote at x equals 0. Okay, so some similar information on this one as we did for the exponential. The domain, notice, is 0 to positive infinity. And in the last video, I mentioned the domains and ranges of the function and its inverse will be flip-flop because that's how we came up with it, right? We interchanged the x's and the y's. So the range would also then be flip-flopped. The range would be the domain of the exponential. Here we're increasing again on the entire domain. And then the limit questions would include going to positive infinity, which is clear that it's positive infinity. The other one, though, wouldn't be negative infinity because of the domain. And in fact, we would want to go 0, but only from the right, right? Because coming from the left, it wouldn't exist. So the limit of a log approaching 0 from the right, in this case, approaching 0 from the right, you can see we would end up at our negative infinity. And so there's just, again, a nice review, if anything, of these logarithmic functions from college algebra.